We have defined the mixed strategy in the previous module, which means that there is a probability distribution. A mixed strategy is a probability distribution over all the pure strategies that a player has. So in some sense, probabilistically you are mixing all the strategies, and that's why the name mixed strategy. Now, once we have developed the notion of mixed strategy, it is also very natural to ask about the equilibrium notion. And the equilibrium that we are going to discuss in this case is called the mixed strategy Nash equilibrium, or MSNE in short. So what is a mixed strategy Nash equilibrium? It is very similar to the pure strategy Nash equilibrium. The difference being that we are now using the profile, the strategy profile, where all the players are choosing mixed strategies instead of a pure strategy. And the definition remains almost equivalent. So if all the other players except I, so if you are focusing on player I, all the players except I are already playing the mixed strategy profile sigma minus I star, and player I is considering to deviate from its own strategy sigma I star to sigma I prime, where sigma I prime is some other strategy. So any other strategy in the set of strategies, in the set of mixed strategies for player I, then that utility, so this player I is not going to get better off, and that is the definition of mixed strategy Nash equilibrium. This inequality should hold for every agent I in N, and if that happens, then we call this strategy profile sigma I star, sigma minus I star to be a mixed strategy Nash equilibrium. Now, it's very natural to draw the relationship between pure strategy Nash equilibrium and mixed strategy Nash equilibrium. You can very easily see that the pure strategy Nash equilibrium is a very special case of mixed strategy Nash equilibrium. The case where it puts a degenerate probability distribution on the strategy set. So in pure strategies, the whole probability mass is concentrated on one specific strategy. And when all the players are doing that, then the equilibrium that you get is a pure strategy Nash equilibrium. You can think of that equivalently in the mixed strategy world as the probability being exactly equal to 1 for that strategy. So therefore, pure strategy Nash equilibrium is by definition a special case of the mixed strategy Nash equilibrium. So all the games that has pure strategy Nash equilibrium definitely has a mixed strategy Nash equilibrium, but the converse might not be true. Alright, so the next definition that we are going to give, or next result that we are going to give, is essentially establishing an alternative definition for mixed strategy Nash equilibrium. So oftentimes we'll see that this definition of mixed strategy Nash equilibrium is more appropriate and easier to use for certain proof of a theorem. So let us first state that result formally. So a mixed strategy profile, sigma I star, sigma minus I star, is a mixed strategy Nash equilibrium if and only if, so this is a necessary and sufficient condition. To write the same inequality, what you replace is, instead of the strategy of player I, which was a mixed strategy in the original definition, so in this original definition, it was a mixed strategy. Now what we are changing is, this is going to be a pure strategy. And we are definitely overloading this notation UI. So what it means is that when you write UI SI sigma minus I, this is nothing but the probability. So we are taking the sum over the probability mass. So I am using the shorthand notation, the sigma minus I of S minus I. That means this is just the product of the corresponding sigma j, sigma k's, and corresponding s j's, s k's, which are the probability of choosing that particular strategy. So essentially there will be n minus 1 summations. So just for a shorthand, I am using this short notation. S minus I is living in the capital S minus I, and then you are taking the utility of SI. So this is the same SI that player I has picked, and all the other players are picking this S minus i's. So what it does is, it is picking the utility when player I is playing SI and the other players are choosing S minus I, and multiplying with the probability of choosing that S minus I and taking its expected sum. So the expected utility of player I when it is choosing the pure strategy Si and all the other players are choosing the mixed strategy sigma minus I, is given by this number. That is what we mean on the right hand side in this inequality. Alright, so it says that how does this definition or this necessary and sufficient condition change anything? It is just saying that instead of looking at all possible mixed strategies, which is an uncountably large set, you are sufficient. It is sufficient to look at only a finite set. You can only look at the strategies in your strategy set, which is finite. The strategy set is finite. We have assumed that. So that verification will ensure that this is a mixed strategy Nash equilibrium, and that is the advantage of using this equivalent definition. So why are we calling it an equivalent definition? Because it's a necessary and sufficient condition. If it is, if you use this as a definition, then there is no change, because MSNE is this, and this also means MSNE. Okay, so let's try to prove this. First, prove the only if direction of the necessary direction. That is quite obvious that SI is a special case. So we are in this direction. What are we trying to prove? We are trying to prove that if it is an MSNE by this original definition of MSNE, then definitely this inequality should hold. This will hold because SI is a special case. You can just think of SI as a degenerate case of that probability distribution. Now the interesting direction is the other direction, where we are given this inequality. This inequality holds for every SI in capital SI and for every agent I in N. Then we will have to show that this is a mixed strategy Nash equilibrium according to this original definition, according to this definition. So we'll have to start with this bunch of inequalities here, and we'll have to show this inequality. So let us try to do that. So first, let us look at the right hand side. So we will somehow have to arrive at this expression here. So let's write down what is the utility when player I is choosing a mixed strategy of sigma I and other players are choosing a mixed strategy profile of sigma minus I star. So by the definition, you can write it as sigma I of SI. I'm just looking at player I's mixed strategy, multiplying that with the utility when player I is picking that pure strategy and other players are picking a mixed strategy of sigma minus I star, and taking the sum over all SIs. So this is this equality. So this is the same thing as the left hand side. Now what we have already seen or already know, because we are given this particular expression, is that this is going to be less than or equal to. So this is actually coming from the given condition. This is less than or equal to ui of sigma I star, sigma minus I star. Now this sigma I star and sigma minus I star are very special strategies, very special mixed strategies. So they do not depend on this SI anymore. So if you look at this particular expression, ui sigma I star, sigma minus I star, that is completely independent of SI. So therefore in this summation I can take that quantity outside this summation. Okay, so once we do that, then this we are only left with this expression, and we know it what this value is. This is a probability distribution, and essentially you are summing over all possible realizations of that random variable. So therefore this will definitely be equal to 1. So the right hand side becomes ui of sigma I star, sigma minus I star. So that essentially proves this fact that you are this is the sigma I. So the sigma I star, sigma minus I star is essentially a mixed strategy Nash equilibrium. So we can use that definition, the inequality, as an equivalent definition of mixed strategy Nash equilibrium. Let us first look at some examples of mixed strategy Nash equilibrium in some of the games that we have already seen. So this game of penalty shootout we have already seen, and let us try to see whether this mixed strategy profile where player 1 sigma 1 is 2/3 and 1/3 for these two strategies L and R, and sigma 2 is this mixed strategy 4/5 and 1/5 for player 2. If we say that this is a mixed strategy Nash equilibrium, we should be able to prove that. If it is not, then we should be able to provide a counterexample. So the first thing that we observe is that if you look at player 2, right? So player 2 and look at the two different strategies it has, L and R. What is the expected utility of player 2? So you can write this as utility of player 2 when that player, second player is choosing L and the first player is choosing this sigma 1. So just I'm using the same sigma 1 here, which means that 2/3 and 1/3. And contrast that with the same utility of player 2 when player 1 is choosing sigma 1 and the other player is choosing R. Second player is choosing R. So you can see that this is going to be, you are going to multiply this utility. So because we are looking at player 2, so this utility with 2/3 and minus 1 with 1/3, that is going to give you 1/3, which is the expected utility. So this utility is going to be 1/3. While this utility, you can calculate that, is going to be minus 1/3. So if you are a rational player, then why should you even play R? Because in the world where player 1 is mixing these two strategies L and R in this way, then player 1 should not be playing R at all, because this is going to give them minus 1/3, and this is going to give 1/3. Any probability mass, any epsilon amount of probability mass, if you can move from R to L, that is going to give you some benefit, because L gives you a larger expected utility. So therefore there is no reason for player 2 to stick to this this mixed strategy of 4/5 and 1/5. It will essentially turn to the other one. And so therefore this is definitely not an equilibrium point. And for that very reason, we can conclude that this strategy profile is not a mixed strategy Nash equilibrium. So we'll have to find something else. Essentially, the whole intuition that I'm trying to give you here is that there needs to be some amount of balance. So if these two numbers, so here it is 1/3 and minus 1/3, if these two numbers were equal, then there was no reason for any of this for player 2 to move its probability mass from one to another. It does not gain anything. And that should also have happened for player 1. Then it would have been a sort of a equilibrium point. So this example essentially gives us some sort of a intuition that this expected utility over these two different strategies should be somewhat equal. Otherwise there is no reason for this player to play the strategy which is giving less expected utility. So if you change these probability masses to half and half for both these players, now this is a different sigma 1, so let's say sigma 1 tilde and sigma 2 tilde, this has changed. Now you can see that the previous condition that we have given, so now you can look at the same expected utility of player 2 for when player 1 is choosing sigma 1 tilde and it is choosing L, that is going to be equal to U2 when player 1 is choosing sigma 1 and it is choosing R. And this actually gives a kind of a foundational result for the characterization of mixed strategy Nash equilibrium. If it is a mixed strategy Nash equilibrium, then something like this has to happen, and that is what we are going to see in the next lecture.